So as we wrap up Unit 7, let's kind of think about just for a moment what we've done so far. First, we spent 2 days solving differential equations algebraically. Then we spent the last 2 or 3 days solving differential equations graphically with slope fields. Today and tomorrow, we're going to talk about applications of these differential equations. So today specifically, we're going to be talking about exponential growth and decay. So I want to remind you, just a moment, I'm going to go down to this bottom right-hand slide to remind you that we've been talking about exponential functions for years. So let's just kind of jot ourselves a note here. Exponential functions or exponential growth and decay. We started off in Algebra 1 with this y equals a times b to the x. And we said a is your starting amount and b is your multiplier. Great. And then we even in pre-calc started saying, gosh, what if you don't know your multiplier? That kind of makes more of a pain. So we said we can change the base. This was a big discussion last year in chapter 8. So we can make the base our new natural base of e, but that's going to then change our exponent. E to the k is the same as b. By the way, we also started using t for time, so we had y equals a times e to the kt. And at some point we said this is fine, and by the way, it was our PERT formula when we were talking about money, right? So we had the initial or the final amount equals the initial amount times e to the rt. And so that's exactly what this is. This is the starting value, just like it was up here. And we said, why are we using 2 different letters for that? Right? This is the starting value, this is the ending value. So we just said, let's give this a new name and let's call it y sub 0, which we also call y naught. So this again, this is something we spent a lot of time on in pre-calc. Saying if you know you have exponential growth and decay, you can use this function, this formula. Keeping in mind that if something is exponentially increasing, it's going to look like this, where this is my starting amount. By the way, we don't talk about negative times. We don't even look at that part of the graph. If we have exponential decay, that means we're starting and my exponential graph is going downhill, meaning the amount of stuff is decreasing. So just kind of giving you a general reminder of what we're doing there. So for us, as we were talking about exponential growth and decay, we talked a lot about money and populations and bacteria. And what we never really said was this relationship that's more of a calculus relationship. It says in these applications, in many of them, not all, the quantity of something, so the amount of money, the number of bacteria, changes at a rate that is proportional to the present amount. So the rate of change of y, let's write that down, dy dt, the rate of change of y, we talked about change over time, is proportional to the current amount of stuff you have, which the amount is y. And so what this is saying is that the rate depends on how much you currently have. So it says the more money in the bank, the faster the rate, the faster it grows. And we can even think about that back here with our picture, right? If we're talking about money going uphill, the slope is getting steeper. As time goes on and the more money we have, the steeper the graph gets. So the rate gets bigger, okay? All right, so what we're going to do is we're going to take that statement that was in bold, that differential equation, dy dt equals ky, and we're going to solve the differential equation using a very generic initial condition, y of 0 equals y naught, which is the point 0 comma y naught, meaning when time is 0, the amount of stuff we have is called y sub 0. So we'll do that kind of at the end. But this is now back where we started this unit, right? So I'm going to take the t to the other side, multiply both sides by dt, And I'm going to divide both sides by y. It's not a very good color to use, is it? So I have a 1 over y times dy, I'll switch that out in a second, equals a k times dt. So on the left I have my y's, and on the right my variable is t. I know you can't really see that. Poor choice of pens, I know. K, by the way, is a constant. It's the constant of proportionality, okay? All right, so here we go. We have the natural log of the absolute value of y on the left, and on the right, the antiderivative of a constant is kt. And then we have our plus c. So now that we've taken the antiderivative, we've been saying for days, we have two things we need to do. One, we need to get y by itself, and the other one is we need to find the value for c. And it is absolutely our decision when we do those things. I do it case by case. So I am personally going to choose to get y by itself. So we're going to spiral out of that logarithm. So I have e to the kt plus c equals the absolute value of y. And we've done all of this before in different problems. Okay, so we need to get rid of that absolute value, so I'm going to go put a plus or minus on the other side. But, you know, usually we use that initial condition to make the decision about the plus or minus. But if we don't know the initial amount, how do we make a choice? Well, we think about it. It's an application problem. Y represents the amount of stuff, whether it's money, bacteria, you know, the amount of a radioactive element. We don't have negative amounts, which means we're not going to use the negative. So I'm going to come up here now. So I've got y equals the positive e to the kt plus c. Now, I'm still kind of focusing on this c, or at some point I need to find it. And just like we did back in lesson 1, I'm going to take this exponent that has addition in it, and I'm going to break it back up into two exponential expressions with multiplication. And why do I do that? Because then we can clean this up. I have a constant raised to a constant, which is still a constant. It's a new constant, but it's just a giant C. So I'm just going to switch the order. So I have y equals C times e to the kt. So I got y by itself, I cleaned up my exponent a little bit, and now I'm ready to plug in my initial condition. So when time is 0, the y value is called y naught. Because we're just trying to understand what this c is. Like, is it just a random number? We're going to find out very quickly it is not. So I have e to the 0, which is 1, which means c, when it's out here in front, not when it's up here, but when c is out in front, represents the initial amount. So I have y equals y naught times e to the kt. Wait a second, that looks awfully familiar because that's how we started today. We started talking about, hold on, these exponential functions from the last few years and how we ended in pre-calc using this version. Well, now we start to see this version comes from this differential equation statement that was made on slide number 1. This is a big deal for us, so I'm going to take a little bit of room to write this down. I didn't leave myself a whole lot of room. Let's go back to slide number 1. Here's the thing. When you see this as your differential equation, we get to skip all of the calculus then, because now we know the solution is that y equals y naught e to the kt. That's a big deal. So if your differential equation is this, then your solution is that. So today's lesson is going to be very calculus light because we just did all of the calculus, and we front loaded it and we found the answer. We found the solution. Okay. All right, so let's take a look at this first example. It says a puppy weighs 2.1 pounds at birth and 3.4 pounds 2 months later. if the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, then how much will the puppy weigh when it is 3 months old? So I started circling some words as I was reading, and that's a big deal. The rate of change of the weight. So I'm going to use W's for weight so it makes more sense. So the rate of change of the weight over time, dW dt, is proportional to the puppy's weight. So dW dt equals K times W. That is what they told us in words. And it looks identical to this up here, except I use W's instead of Y's. That's okay. The good news is because this is what we have, we know our solution. We know our antiderivative. So we're going to skip all of the calculus and say W equals W naught times e to the kt. And now this is no longer a calculus question. We used calculus to interpret the question, to decipher what it was saying. Now everything else is something we've done before. I like myself a little timeline. When the puppy was born, it was 2.1 pounds. 2 months later, so when time is 2, it was 3.4 pounds. And the question is, how much will it weigh when time is 3? Well, I kind of have an equation. If I want to find the weight, well, I need the time for sure, but I also need to fill in K and W naught, which is great, right? This right here, there's my initial weight. There's my W naught. This extra piece of information, we're going to use it to find our K value. So you saw something just like this in homework where it wasn't a calculus question. So I have W equals 2.1 times e to the kt. And now I'm going to go plug in my additional point. So the weight is 3.4 when time is 2. And so you have 3 choices right now. We need to find K. And so you decide, do you want to solve for K by hand or with a calculator? And if you choose a calculator, you choose if you use the solver or a graph. It's your choice. To be honest, I think it's a lot faster just to solve this by hand. That's my choice. So you can use a solver. I'll do it on the next one. But I'm going to divide both sides by 2.1. Then I'm going to take the natural log of both sides. By the way, if you want, you can call that 34 over 21. It's the same thing. So I have K equals 1/2 times the natural log of 3.4 over 2.1. Can you even see that? So sorry. So I have my calculator off to the side here, and so I'm quite literally just going to type that in, 0.5, just to make it a decimal. 0.5 times the natural log of 3.4 divided by 2.1. And so I have K is approximately equal to 0.241. Now, that is not my final answer, so I would like to save that. So I hit that store button. You know what? I'm going to use K because, well, that's what it's called on my paper. It makes sense. Okay, I know we're just kind of running out of room here, so I'm going to slide over here. So I'm going to take that K value and I'm going to go throw it right back up into my equation. So I have W equals 2.1 times e to the 0.241t. But I am going to remind myself that that K value is stored in my calculator. Okay, well now we're finally ready to answer the question. How much does the puppy weigh when it is 3 months old? So W equals 2.1 times e to the 0.241 times 3. And I'm going to go back to my calculator and type that in. So I guess I didn't need to store it. I'll just go grab it. Oh, no, just kidding. I don't know what I was thinking. I need 2.1 times e to the, and now I'm just going to go put that K in there, times 3. And so the weight of that puppy is 4.326 pounds. So sorry for kind of cramming everything in there. Clearly I had given us extra space, but then I used it, that last slide there. All right, let's flip it over. Okay, so it says a dose of 450 milligrams of penicillin is administered to a patient. The amount of penicillin in milligrams in the bloodstream at time t, in hours, is given by a function called A of t. The rate at which the drug leaves the bloodstream, so the derivative, can be modeled by, the differential equation dA dt equals k times A, where k is a constant. You know, I am going to stop right there because that looks exactly like our differential equation from the front, except instead of using y's, dy dt equals ky, they used capital A's. But that doesn't change the fact that when I see that as my differential equation, we know the solution is that, I'm going to say PERT formula because it's less syllables, but it's that A equals A naught times e to the kt. Great. I guess I should keep reading. It says after 7 hours, only 50 milligrams of penicillin remain in the bloodstream. Write an equation for A of t. I mean, I just called it A, but A of t means the amount of penicillin in terms of the time. Right now I have T's and K's, and so I'm going to fill it all in. Okay, so let's get ourselves a little timeline here. We've got time 0. We start the clock with that initial dose, 450 milligrams. So at time 0 when that clock starts, we have 450 milligrams of penicillin in the blood. Then they tell us after 7 hours, we have 50 milligrams. All right, well, this is the amount at time 0, so that's my A naught. And this I'm going to use to find K. All right, here we go. So I have A equals 450 times e to the kt. There's my initial amount put in. And now let's put in this point. So the amount is 50 when the time is 7. So I did the last one by hand. I'm going to do this one with my solver. So I'm going to hit my math button and I'm going to go to the very bottom. And your solver might look different. And we could spend 20 minutes talking about how different all the solvers are and what they all look like. If you have a question on your solver, come see me. But this is saying we're going to put the left side in the first box and I'm going to put the right side in the second box. And I'm going to use K's. Well, that's not a K. Times 7. All right, so right now that K is just still hanging out from when I used the solver on the front side earlier today, but that's not the answer. So it's waiting for us to solve, and so it even tells you at the top, press alpha solve. Hit the alpha button and then the enter button. And so there's my K value. K equals negative 0.314. Not surprised that K is negative because the amount of penicillin is decreasing, so the rate should be negative. And the only way this can be negative is if K is negative because the amount of penicillin is not, right? So that doesn't surprise me. So right now I can say A of t, the amount of penicillin at any time, equals, I'm just going back here, equals 450 times e to the negative 0.314 t. Now, just like on the front, I'm going to make sure I note that I am going to store that in my calculator. Actually, when you use the solver and you don't use an X, it automatically saves that K value. So I don't need to go like store it. It's already there. Okay. All right. Now this may look different than the notes I handed out in class because the notes you got probably just have this on it, which is fine. I decided to add an extra question, and I had decided to ask us to add some units of measure. So it says, how fast is the penicillin leaving the bloodstream after 7 hours? So I look at that word, is it how fast? Oh, they're asking for a rate. They're asking for a derivative. So they're saying find dA dt when t equals 7. great news. That's how we started this question. They gave us the derivative. We just had to go find k, but now we have it. Okay, well, let's go back here. I'm going to do this a couple of different ways, but I have dA dt equals negative 0.314 times a. It is different for us because all year when we've been finding the slope, we're like, oh, you just need the x value or the time. Well, there's nowhere for me to plug the time in. It says the rate depends on the amount. So I need the amount of penicillin at the instance when time is 7. Perfect. We know that. At time 7, the amount is 50. So if I want to find that rate, I just need to plug the amount in. So I'm going to grab my calculator. I'm going to get out of the solver. I'm going to bring that k value back up, and I'm going to multiply it by 50. And I get negative 15.694. I want us to indicate units of measure. Well, let's go back to here. This is what we found, dA dt. A, the amount of penicillin, it's being measured in milligrams, over t. T is time, t is being measured in hours. Okay, so that's one way to do it. Here in a few moments we'll talk about another option as well. So now let's go to that question that was actually on your paper. It says, how fast is the penicillin leaving the bloodstream after 1 hour? So, I mean, it's the same question. I want to find dA dt now when time is 1. Well, we have a formula for dA dt. It's negative 0.314 times a. And I'm just writing the same thing down that I did above. However, we're going, oh, we need the amount of penicillin when time is 1. That we don't have. Look at our timeline. We know the amount at time 0. We know the amount at time 7. That's okay, because we have a formula that tells us how to do that, don't we? Perfect. So let's use A of t from our previous slide to find A of 1. So I'm just going to go to my calculator. I don't need a solver for this. I'm just going to go plug a 1 in here. So I have 450 times e to the k, I'm not using that rounded value, times 1. That's the amount. Not that we needed it, but when time is 1, we had 328.770 milligrams. And by the way, this is like the longest way to do this second question. That's okay. I was just kind of keeping it consistent. So my rate is that k value times 328.770. Which again, I'm not using, sorry, you can't see that. I'm not using negative 0.314. I keep using that k value, right? So my rate after 1 hour is negative 103.197. But we're still in milligrams per hour. Now, I mean, it wasn't a hard question. In fact, after doing this question, it just made sense to do it the same way. But I want to point out we didn't have to do it that way. What we felt kind of interesting about these two questions is that they gave us the time, but the derivative that we had needed the amount of penicillin. I was like, wow, we can do this an old way. I want to know the rate of change of the amount of penicillin. Why can't I just take the derivative of my equation over here and plug in a 1? I mean, wouldn't it be the same thing? And let's go back to our calculator. Let's just say, hey, calculator, take the derivative, math 8. Let's use t's. So I have d dt of the formula or the function that we wrote. I'm going to put my k in there. At time 1. I mean, I'm not surprised to get the same answer. It represents the same thing. I just got there differently, right? It's a different kind of method, but it still gives us the derivative of A. Okay. All right, let's take a look at this last question. So it says a radioactive element decays according to this differential equation. And I added this in, where Y is measured in grams and T is in years. Find the half-life for this particular element. So what I reminded you of, even though it's in your homework, is the half-life of an element is the amount of time it takes for half of the substance to decay. Well, we feel like we're missing a lot of information. So at time equals 0, I don't know how much we have. The initial amount they did not tell me. But my question is, how long does it take until I'm left with half of Y naught? Okay, let's back up. My differential equation, dy dt equals a constant times y. Perfect. I know the antiderivative to that, and they gave me k. So we've got our PERT formula, but they already gave us our k value. Okay, but again, we don't know why not. That's okay. We're just trying to find how long it takes till we're left with half of that. So my new amount is half of y naught. And the only thing left for us to do is solve for time. So let's divide both sides by y naught. And I'm left with 1/2 equals e to the negative 0.124t. And you can solve that however you like. You can use the solver, you can use a graph, you can do it by hand. In fact, I'm going to do it by hand because it's faster for me. So I have the natural log of 1/2 equals negative 0.124t. And if I divide by my negative 0.124, I have the natural log of 0.5 divided by negative 0.124. I just typed that in, and I get 5.590. And we found a time, and it says time is being measured in years. So even though we didn't have the exact starting value, we could have started with anything. You could have said, I'm starting with 100%, and I'm going to be left with 50%. At some point, we would have landed with a 1/2 over here.